I want to sort of pick up where I left off from yesterday. I don't think I'm going to talk the entire time today, so hopefully I won't have that much to say today. What I do want to talk about is sort of the unbounded case of what we're working on. And then I think tomorrow I'm going to talk a little bit about, I'm basically going to walk through some complete examples where it's stated as a word problem, and we'll set up the problem, we'll graph the constraints, we'll find the corner points, we'll find the min and max and everything. So we'll do a couple complete problems, I think, tomorrow. So just a heads up of where we're going. So for today, I want to continue from where we were yesterday. So yesterday, I taught you guys basically how we're solving these linear programming problems now. So just a refresh of what we did really quick is we had our objective function. So given our objective function, and constraints, or maybe we have to find them. But once we have our constraints and objective function, what did we have to do? Well, we graphed the constraints. Again, the constraints were a system of inequalities. So we're graphing a system of inequalities. I guess I don't want this in the past tense. Graph the constraints. And then once we do that, we look for corner points of the feasible set. So corner points. And I told you that we're trying to, if we're trying to find the min or the max of our objective function, I told you that if it has a minimum or maximum, and in the case of yesterday, we dealt with bounded feasible sets, in which case it definitely does have a minimum or maximum, then those had to happen at the corner points. So we just test our objective function at the corner points, i.e. we plug the corner points into our objective function, which I usually call P. So P is the objective function. So we just plug in the corner points one by one, and we just take a look at the values that we get, and then we just indicate which was the biggest and which was the smallest, the min / max, depending on what the problem asked for. So if the problem asked for the minimum, I just look for the smallest value that I got by plugging in the corner points. And I'll just point out that this was for bounded feasible sets. So again, that's when your feasible set makes a closed shape. In that case, I only have to look at the corner points. I just plug them into the objective function and I find the min or max value from there. Okay, so I did a couple examples of this yesterday. What I want to talk about now is, what do you do if it's not bounded? What if it's not bounded? And, oh, my computer's not, hang on. Ooh, that was dangerous. My laptop wasn't plugged in, so it almost died on us in the middle of lecture. That would have been bad. Glad I caught that. Okay, so what do we do if the feasible set is not bounded? What do we do? That's what I want to talk about and do a couple examples of. Because if it's not bounded, it's just a little trickier to deal with. So for an unbounded feasible set, and there are some examples of this on your activity, probably on your web work. So I just want to make sure I talk about this here. So again, what does that look like? An unbounded feasible set means that your feasible set does not make a closed shape. So maybe it does something like, if the shaded part is your feasible set, maybe it does something like this, right? It doesn't close off ever, it just kind of goes off forever. Yeah, that would be something unbounded. It does not make a closed shape. So what do we do in this situation? Why is this situation bad? The problem is, so here's our issue, is that the minimum / max of the objective function P may not exist. There may not be a minimum or maximum at all. Because of this being unbounded, it means it goes off forever in some direction. If I go out far enough, I just keep going off and keep plugging in points from really far away, P might get really big and never stop growing. It might just grow without bound. And so there might not be a maximum because it just keeps getting bigger and bigger as I go off in some direction. Or it might get smaller and smaller or more negative as I go off in one direction and never stop. So there may not be a minimum or maximum just because of the fact that it's unbounded means that the objective function means that it can sort of grow or get smaller without stopping, right? There's nowhere it ever gets capped off. And so that raises some issues that we have to deal with. Now, the min or max may exist, and here's our fact. If the minimum and maximum do exist, then they happen at a corner point again. So the min and max may not exist at all, but if they do happen to exist, then they happen at a corner point again. So still corner points are, where we want to check for even an unbounded feasible set. But we just have to be a little extra careful and check some extra points too. Basically what we're going to do is we're going to still check the corner points, but then I'm going to check some extra points on these sort of unbounded parts that go off forever to see if my function is either getting bigger or smaller away from the corner points. So that's what we're going to do. So let me write down our procedure, and then I'm going to do some examples. So here's our procedure for unbounded. I mean, no matter what, we still have to graph the constraints and then find the corner points. So I still need to find the corner points. And I still need to plug corner points into the function. So this part doesn't change from before. I still have to test it at the corner points. But here's the extra step, maybe extra 2 steps, is I need to pick a point. I'm going to think about how I want to phrase this to be less confusing, or I don't know. Anyway, I don't want to be super confusing when I write this sentence. I want to pick a point from these parts of the boundary. So on these lines that go around the shaded part, I want to pick points on the parts that go off forever. And I want those to not be corner points. So I want to just pick some points. So here's how I'm going to write this. We're going to pick a point on each unbounded part of the boundary. And we're going to plug them in. We're going to plug them into our objective function. So the issue with it being unbounded is that maybe as I go along this line forever, the function gets bigger and bigger, or it gets smaller and smaller. And I want to see if that's happening. So I'm going to pick some point on this line that goes off forever, other than the corner point. And I'm going to make sure it's on a part of the line that's touching the, that's around my shaded region. So just pick some point. And I have this other unbounded part. I'm going to pick a point there too. And I'm going to take those 2 points and plug them into my objective function and see what I get. And then if those points, if either of those points are, well, I'll write it this way. If they give bigger values than the corner points, there's no maximum. So if I pick a point up here and I get something bigger than what I got at all of the corner points, then there's no maximum. Because if there is a maximum, it has to happen at a corner point. But if I take something that's not a corner point and I get something bigger than the corner points, well, then there can't be a maximum because it got something bigger at not a corner point. I.e., what that is indicating to us is that as I go up this way, I get some, it just gets, the objective function just gets bigger and bigger without stopping. And so there's no maximum. And the same thing, if it gets smaller, then there's no minimum. So if I plug in one of these points and I get something smaller than what I got at all the corner points, then that means that as I go along this way, the function is getting smaller and smaller without stopping. and so there's no minimum either. Okay. So that is how we're going to treat unbounded feasible sets with our objective functions. We test the corner points, and then I pick a couple extra points on these unbounded parts, and I compare them to the corner points and see what happens. Okay, so I want to do an explicit example. I'll just stop and ask if there are any questions first before I do that. Okay, let's see an explicit example that'll hopefully make this a little clearer than what I put up here. We'll start with a sort of simple, the simplest one I could think of really to fit this criteria, just to illustrate what might happen and how to deal with it. So here's our first example with an unbounded feasible set. Our objective function will be p equals x minus y. So here's our objective function. And here are our constraints. I'm just going to put these two inequalities, x greater than or equal to 0 and y greater than or equal to 0. Just those two. Okay. And I want to just ask the question, does this function have a min or a max subject to these constraints? So if I have these constraints in this function, can I find the minimum or maximum? Or do they just not exist or whatever? So, let's go ahead and graph this system of inequalities just to see what it looks like. And this is like the nicest system of inequalities we could ask for. Nice and simple. The point is that x greater than or equal to 0 says that I just go to the right of the y-axis, and y greater than or equal to 0 says I just go above the x-axis. So I'm just in this quadrant is my feasible set, this entire quadrant. So this whole thing up here, which goes off forever, I don't have an infinite whiteboard, so I can only draw a small portion of it. But this goes off forever, and this is my entire feasible set, this entire quadrant. So just extend these out from the origin forever, and that whole upper right quadrant of the plane is my feasible set. So it's certainly unbounded, because it does not make a closed off shape. It's 1/4 of a plane, so it's infinite. Now, how many corner points do I have? Well, there's only the two lines, and they intersect in one point. So there's one corner point. It's the origin. 0, 0 is my only corner point. So according to our procedure, I need to first test my function at the corner point. So let's do that. At 0, 0, what is my function? Well, I just plug in 0 for both. Oh, p is just going to be equal to 0, because I'll get 0 minus 0. So at the origin, my function is 0. And so now the question is this a min or a max? Is this a minimum or a maximum? And I can't answer that question yet, because it might be that as I go, say, along this line forever, my function gets really big or really small. And same thing this way. And so I have to check to be sure. And so what I'm going to do now, these are my two unbounded components of the boundary, these two lines that go out. I'm going to take a point from each one, and I'm going to test them in my function. So let's take a point up here first on the y-axis, different from my corner point. It's important that I don't pick the corner point again. I need to pick a different point. So just take any point on the y-axis different from the corner point. So I don't know. Things on the y-axis have coordinate 0, something. Let's just put a number here, some positive number. How about 4? I don't know. It's a number. 0, 4. You can pick any point on the y-axis other than the corner point. So let's just test it and see what happens. At the point 0, 4, what is p? I'm going to get 0 minus 4. So p equals -4. Okay. So now let's compare. Is this bigger or smaller than what I got at the corner point?